Next, let's take a look at the heat flux. Highlight solution in the tree, thermal total heat flux. Right click and say evaluate all results. That'll give me the total heat flux. And let's visualize these as vectors because heat flux is a vector. So I can click on that. And I will, let me increase the size of the vectors. And I see I have a very high heat flow coming in here, and everything else is small compared to that. And that's that makes sense because heat is being lost from this edge, and to keep this edge at 1 degree, it's going to require that you put in a lot of heat over here. We can also visualize this as vectors of equal length. So I can select that. And then I like to use solid form for the symbols. And then I can play around with the size. And what this is doing is it's plotting an arrow at each node. I can see that if I go here and I turn on the elements. So you can see there's an arrow at each node. So at each node it's determining both components of the heat flux. Let's think about that. Let me annotate this. Heat flux is a vector, and so you have the heat flux in the x direction, which is the heat flow per unit area in the x direction, and then you have heat flux similarly in the y direction. And the x component is related to the gradient of the temperature in the x direction, and similarly for the y component. So what it's done is it's gone to the temperature interpolation and it's differentiated it to find qx, and similarly for qy. Remember from the big ideas in FEA that when we differentiate a numerically obtained result, it's going to increase the error. So this, the heat flux is going to have more error than the temperature. In fact, we will see that as we refine the mesh, this value keeps going up. So this value is in fact, I believe it'll go up in an unbounded way as you refine the mesh. And we can use this to check the boundary conditions. So here we have an isothermal boundary condition, which means that the temperature is constant along this line. That means there can be no heat flow along this line, and so the heat has to be perpendicular. So that's a check on that boundary condition. And over here it's insulated, so it can't cross that boundary, and so it's along there. And over here it's along there, and here you get something funky because at the corner you have two directions in which you cannot have heat flux, and this is a very small value, so we'll not worry too much about it. And then you can see that the heat flow, heat is flowing out to the fluid over here. And you can see that though the heat flux is supposed to be 0 at these boundaries, it's actually a very small value. So as we saw, the natural boundary condition is satisfied only approximately, whereas the essential boundary condition is satisfied exactly. And we see the effect of that there. And you can save the project.